Hello, I'm Gabriele Boschetto, and in this video we'll talk to you about how we use atomistic modeling with QuantumATK to simulate strain sensors based on 1D and 2D materials. So this is the outline of the talk, in which I will briefly discuss strain sensors and why we are interested in modeling them. I'm going to present our simulation results and how these are linked with experimental data. And finally, there are conclusions and outlook for the future simulations. Okay, so this work was carried out in the context of an European project called Smart Vista. And the aim of the project actually is to develop a smart multimodal sensor, which is non-invasive and which purpose is to monitor in real time the patient's health status and possible insurgence of cardiovascular diseases, which are currently the leading cause of mortality, not just in Europe, but in the world. The sensor itself, which you can see at the bottom right of the screen, is made itself of smaller sensors, which are based on 1D and 2D nanomaterials, mainly carbon nanotubes and molybdenum disulfide, MoS2. These kind of sensors are able to measure in real time important vital signs, which can be, for example, respiratory and heart rate, the temperature, body temperature, and the concentration of specific biomarkers. Here we focus on strain sensors for monitoring the respiratory rate. Now, this sensor will stretch and relax following the patient respiration, and so there are some requirements, such as high stretchability and flexibility, of course. They have to be compact and small because they are non-invasive. They have to be sensitive and also biocompatible because they will be in direct contact with human skin. As active materials for this sensor, we chose carbon nanotubes and MoS2 as they show desirable properties for this kind of application, as you can see on the right. For example, they have high carrier mobilities. They have the capability of withstand high strain, and they have adjustable sensitivities. To design the sensors, we followed a multidisciplinary approach from materials modeling to fabrication and characterization up to ex-vivo testing, as you can see here. Ultimately, with our simulations, we aim to bridge the gap between material properties and device physics. The main theory behind the working mechanism of strain sensors, which are based on carbon nanotubes, is the percolation theory. Now, essentially, when we have carbon nanotubes in a network, in a disordered network, as in this case, they will form close contacts. These close contacts essentially are conductive pathways in which charge can easily flow, which means high conductivity, electrical conductivity. When we apply strain, as in the situation on the right, we actually break some of these contacts, and thus we hinder the mobility of electrons and we lower the electric conductivity. So these actually, this stretch and relax, this formation and break of close contacts lead to the variation of the network and the material, the sensor, essentially, conductivity. Now, given the complexity of our CNT network, we decided to model a simple array of carbon nanotubes to which we have applied tensor strain. Now, this means that we have step by step increased the intertube distance, and on any step, we computed the effective mass along and across the tubes, as you can see here in this figure. Now, to carry out these atomistic simulations, we use the QuantumATK because it's an easy to use and efficient platform. For example, with its builder tool, it was very easy to build the carbon nanotubes and to construct the network. Moreover, aside from the typical properties of interest with DFT, such as effective mass, density of states, and so on, the built-in effective mass analyzer tool allowed us to easily compute the effective masses along the chosen direction. As I was mentioning before, we computed the effective masses to estimate the electron mobility. Now, lower effective masses mean higher electromobility and high conductivity. Now, as you can see, the parallel effective mass, which is along the carbon nanotube, stays constant when we apply tensor strain. Now, this makes sense because actually we are not stretching here the carbon-carbon bonds, but we are simply varying the intertube distance. On the contrary, the effective mass across the network increases when we increase the intertube distance. And this is consistent with the percolation theory, because actually what happens here is that we are breaking the close contacts and we are hindering the electron mobility. We then moved on to MoS2, whose electronic properties and electrical conductivity can be modulated by direction of strain. Now here we apply strain along the armature and zigzag directions, as you can see on the picture here on the right. At each step, again, we computed both the band gap and of the material and the effective mass along both directions. As you can see, if we start from the band gap, so the plots at the top, there is a great variability in the material's band gap. And if we apply a suitable large equiaxial strain, we even observe a semiconductor to metal transition for MoS2. Regarding effective masses instead, so the plots at the bottom, we can see that the material has an isotropic mobility when it's in equilibrium, so when there is no strain. When we apply strain, actually, this becomes interesting because the mobility becomes anisotropic. And overall, basically, this simulation shows how MoS2 is extremely sensitive to structural deformation, which makes it a suitable material for strain sensors. Okay, so far we discussed about our simulation results, but how can we link these to experiments? Now, what you can see here is an example of the fabrication and testing of our CNT sensor. Now, to fabricate the CNT sensor, we actually encapsulated our CNT network in a conductive polymer matrix, which ensures actually an even greater stretchability and biocompatibility of the sensor. To test the sensor, we then attached it to a motor and we measure its voltage over several stretch and relax cycles. As you can see from the plot at the bottom, we saw quite a significant variation in the voltage of the device, which is explained by the breaking and formation of close contacts. Then we tested these sensors on anesthetized rats, as you can see on the top right. And we measured once again the voltage signal, which in this case can be attributed to the animal respiratory rate. So essentially our DVT simulations, together with this experiment, confirm the percolation theory. Now, to conclude, by following this holistic approach, we actually designed, fabricated, and tested a working carbon nanotube sensor to measure respiratory rate. Now, of course, there were some challenges in our modeling approach. And for instance, the polymer network was not taken into account, as well as the network disorder. Now, in the future, we would like to systematically improve this model in order to include non-uniform deformations, and we would like to fabricate and test also MoS2-based sensor. If you want to know more, please have a look at our publication. As I mentioned at the beginning, this was a collaborative project, so I'd like to acknowledge all the members of the Smart Vista consortium and the HPC facilities to run DFT simulations. And thank you for watching.